So today let us see properties of alkenes. In the previous video, we have seen the preparatory methods of alkenes. So today let us see their properties. So we have physical properties and chemical properties. So what are physical properties of alkenes? So state of alkenes. So from we know alkenes are of the form. Wait, alkenes are of the form CnH2n plus 2. So when N is from 1 to 4, N is from 1 to 4, means methane, ethane, propane, butane. Then the physical state of the alkane is it is gas. From pentane to C16, those are liquids, and the rest of the alkanes are solids. So this is the physical state of alkenes. So when we talk about boiling point of alkane is directly proportional to its molecular weight, and it is directly proportional to number of branches. That is, now let us take an example. Let's take neopentane, and then we take 2-methyl butane, okay, and then we'll take n-pentane. So this will be the boiling point order, decreasing order of boiling point. So neopentane will have the highest boiling point because the branches are more. When there are more branches, the packing between atoms will be better. So melting point. So when we are talking about melting point is also directly proportional to molecular weight. We don't talk about branches in melting point, but there is one exception in melting point, that is even number of alkenes will have a higher melting point than adjacent odd alkenes. That is, we draw a graph like this. So we have hexane, means it is even. Okay, so heptane, which is odd, it has odd number of carbons. So as it has odd number of carbons, it will have less melting point. It will have less melting point. So let's see octane. Octane is again even. So when octane is even, it is higher, and again nonane is down. So even number of carbon containing alkane is has greater melting point than the adjacent odd number containing alkanes. So nonane and heptane will have less than octane. Okay, so this is some example. Now, density of alkanes is directly proportional to molecular weight and then solubility. So alkanes are soluble in non-polar solvents. Non-polar solvents are where CC bond is there. For example, benzene or kerosene. Okay, so let us see chemical properties of alkanes. So alkanes undergo only substitution reactions. What are substitution reactions? Now I am having RH. I react with something and RH is formed. X is something here. Okay. So such kind of reactions are called substitution reactions. So for example, we have in substitution reactions, we are having halogenation, nitration, and sulfonation. Okay, so these are the chemical properties of alkenes. So let us start discussing each. So the first one we have today is halogenation, so which is a very important topic in whole alkenes. So halogenation. See, halogenation is substitution reaction of halogen. Now I take an alkene, I add Cl2 in presence of sunlight. So the substitution reactions generally take place in place of sunlight, or you know free radical mechanism containing things mostly take under sunlight because they undergo under sunlight because this helps in formation of radicals. Okay, now if I take methane and react it with chlorine, so I have different cases. So this chlorine can replace one hydrogen or two hydrogens or three hydrogens or all the four hydrogens. So when the chlorine or the halogen is replacing one of the hydrogen, then it is called monohalogenation. So this is called monohalogenation. And we have dihalogenation, trihalogenation, quaternary halogenation, or okay, so or polyhalogenation. So when one hydrogen is replaced, it will be monohalogenation. And when there is more hydrogen replaced, then will be polyhalogenation. So the halogenation reaction is this means you add Cl2 to alkane in presence of sunlight and then substituted alkane is formed or alkyl halide is formed. Now, this is undergone under free radical mechanism, and then reactivity order is fluorine, chlorine, bromine, iodine. So fluorine will react better than chlorine, than bromine, than iodine here. This is an important. So mechanism of halogenation, it occurs in three steps. So we have chain initiation, we have chain propagation, and then we have chain termination. Okay, chain initiation, chain propagation, and chain termination. So what is the first step? Chain initiation. So the Br2 or the halogen we are using here, it is broken. Okay, homolytic cleavage takes place and each bromine gets its radical. Okay, homolytic cleavage takes place and radicals are formed. So this is chain initiation reaction. So what will be chain propagation? So we are taking an alkane, right? So we are taking an alkane. So we have RCH3. This hydrogen is there with us, and then we have the bromine. So they will react, and then what would happen? This hydrogen will undergo homolytic cleavage. This will get a free radical, this will get a free radical, and then HBr is reacted and R radical is formed. You can understand that. Okay. R radical is formed and then HBr is formed. Here, homolytic cleavage takes place. And then similarly, the same R will again react with BrBr, and here also bromine-bromine free radical is formed, and then RBr plus bromine radical is formed. So that is why once a free radical reaction has started, it is really hard to stop it because radicals keep forming and products keep forming. So this is chain propagation. So the products are formed. Once there are enough radicals for you, chain termination takes place. That is, R and R will combine to form RR, or BR form BR, and then R radical and BR radical form RBR. This is the product we are looking for. This is called chain termination, where all the radicals combine to form various products. So we have chain initiation, chain propagation, and then chain termination. Now, major product and minor product. If any question is going to come from halogenation reactions, that would be the major product and minor product. So this major product and minor product is based on the stability. Now, for example, we have seen an example here. We are taking propane and we are reacting it with chlorine. So there are two cases. This chlorine can attack here at this carbon, or it can attack here. Out of these two, what will chlorine select? That we will discuss under this topic. Okay. So we have two cases. It is reacting the primary carbon or it is reacting with the secondary carbon. Let us see. So this is chlorination, this is bromination. Iodination is not an ideal process. So we only discuss chlorination and bromination whenever we are talking about reactivity. So what is this table? This is considered to be a meaningless table, but questions are going to come on this. That is, how do you read this table? This is called reactivity order of halogenation. That is, now let me do chlorination. Now, what is the probability or the reactivity? Okay, probability or the reactivity that the chlorine in the halogenation will replace the primary hydrogen, it will replace a secondary hydrogen, or it will replace a tertiary hydrogen. Or the bromine. In case of bromination, the bromine which will replace the primary hydrogen or secondary hydrogen or the tertiary hydrogen. So, how do we calculate this? These are some values which we have to remember. Using this, we will find the percentage of the product. So, how do we find the percentage of the product? We will see. So, chlorination, the reactivity for 1 degree hydrogen is 1. Then for 2 degree hydrogen is 3.5. And 3 degree hydrogen is 5. For bromination, it's 1, 82, and 1600. So in some books, it is also given as 3.8. So for now, we are taking 3.5. Now, we are taking cyclopropane. We are taking propane reacting with chlorine. So here it is replacing a primary hydrogen. Here it is replacing a secondary hydrogen. Now, we have seen here primary and secondary chlorination. For primary, what is the reactivity? 1. For secondary, it is 3.5. So, what are the total number of primary hydrogens here? Means how many hydrogens are there which chlorine can replace? Primary hydrogens. So, here we can see there are 6 hydrogens, right? So, we have 3 here, 3 here. 3 plus 3, 6. We have 6 primary hydrogens. And number of secondary hydrogens are 2. So the probability is that the chlorine can go and attack the primary hydrogen or the chlorine can go and attack the secondary hydrogen. So we have seen a reactivity table here. So what will be the reactivity of the 6 hydrogens? It will be 6 into 1 primary hydrogens. What about the secondary hydrogens? Each hydrogen can contribute up to 3.5 reactivity. So 2 into 3.5. So 7 will be reactivity of the secondary hydrogens. So we will find the percentage of product. So a hypothetical formula, this is basically a meaningless calculation, but then also we will find percentage product is like reactivity of primary hydrogen by total reactivity into 100. So that's how we'll calculate this. Now we have calculated the reactivities of primary hydrogen and secondary hydrogen, right? So it is 6 and it is 7. Now, finding the percentage product is very simple. So we will do 6 by 6 plus 7 into 100 and then 7 by 7 plus 6 plus 7 into 100. This is 7 by 6 plus 7 into 100 is when it replaces the secondary hydrogen. Means the chlorine, when it replaces the secondary hydrogen, means this product. We are speaking about this product, right? So what will be the percentage of the product? So whenever such kind of possibilities are there, both the products are formed, one will be major and one will be minor. So when we calculate these percentages, we can find it. So 6 by 13. So we'll get some 46% here and 54% here. So the major product here is the secondary hydrogen replacing the border margin is not that much, but then also for the problem purpose, we are telling this will be 46%, means this is the minor product, and this is 54%, which is the major product. Okay, that's how we will do any numerical based on reactivity. So let's see another example of bromination here. So we are taking propane and then reacting it with bromine. So we know that Hn. Okay, here also write Hn. So you are doing bromination. So bromine can go and attack the primary hydrogen or the secondary hydrogen. You can substitute a primary hydrogen or a secondary hydrogen. Now let's calculate the reactivity. So number of primary hydrogens that can be replaceable are, we have 6 primary hydrogens, right? And the reactivity of primary hydrogen is 1. What is the bromination table? 1, 182 and 1600, right? Yeah. 182 and 1600. No. The reactivity of primary hydrogen is 6. So secondary hydrogen. In case of secondary hydrogen, how many secondary hydrogens we have? 2 secondary hydrogens. And then what is the reactivity of each secondary hydrogen? 82. We have seen in the table. It is 82. So we will do 2 into 82, which will be 164. Okay. So let us find the percentage product. For primary hydrogen or this one, the percentage product will be replaceability of the primary hydrogen by total reactivity, which will be 170 into 100. Okay, so 6 into 100 divided by 170. Right. So we are getting 3.5%. So the other will be 100 minus 3.5%, which will be 96.5%. You can calculate like that also for secondary hydrogen. You can do 164 by 170 into 100, which will be 96.5. So here we have 3.5%. 3.5 of the total product, 3.5% will be this compound, 96.5% will be the other compound. So of course, this is major, this is minor. You see here, when we are talking about chlorine, the border between these two values is very less. But here the border between these two values is very high. So the negligible amount, the primary hydrogen replacement is very negligible amount. So we can draw some conclusions here, and that conclusions we discuss under Hammond's postulate. So what is Hammond's postulate? It compares bromination with chlorination. It simply tells that bromination is regioselective. Means bromination, it is like more regioselective. Like it is very dominantly choosing 2 degree over 1 degree. While chlorination, the border is not that much. Okay, so it compares bromination with chlorination. So we will see the um, transition state of chlorination and bromination. So chlorination is exothermic and bromination is endothermic. Now, see here. So this is the reaction coordinate and this is the time. So as the time goes further, how is the reaction proceeding? So we can clearly see here. So let me use some light. So as the reaction is proceeding, it has reached one transition state. So this is the concentration of reactants first. So it has reached one transition state. Okay. And then it has reached another transition state. And the energy of the reactant, the product. So here the product is formed. The energy of the product is less than the energy of reactant. What does that mean? Heat has been released. So when the heat has been released, what is the reaction? Exothermic reaction. So the transition state formed here, the transition state is looking towards the products. Okay. The transition state is looking towards products. So that is Hammond's postulate. In case of chlorination, in case of bromination, you can see as the reaction is proceeding, first transition state is occurred, second transition state is occurred, and products are formed here. So the products are formed here. So we can see products are formed there. And delta H is positive, right? So this is the energy of reactants, this is the energy of products. Means energy of products is greater than energy of reactants. That is, energy has been absorbed. So when energy is absorbed, it is endothermic. So bromination is endothermic. And when we see at the transition state, what is nearer to transition state? The products are near to the transition state, right? So the transition state looks towards the products. So you can understand like this. So bromine is more wiser than chlorine. So bromine thinks about its end product, but chlorine does not. Chlorine wants to react faster. It wants to make friends. But bromine, it is wiser. It will choose some good friends. So something like that. So bromination is regioselective, very, very important. Okay? Because bromination is thermodynamically driven and chlorination is kinetically driven. And when reactivity is more, selectivity is less. Means chlorination reactivity is more. It is exothermic. It wants to react fast. So that is why it is not selecting. It wants to react somehow. But in case of bromination, so in case of bromination, it wants to it wants to select. Like it wants to be stable. So bromination is thermodynamically driven, right? So when reactivity is more, selectivity is less. That applies to chlorine. So we have some other reactions where a halogen is replaced here. Okay. So let me just sorry. Okay. So there are some other reactions. So when you take cyclohexane react with SO2Cl2, there is also a form of halogenation. So chlorine is going to attack. Okay. What is the reagent here? Dibenzenoyl peroxide with heat. Okay. And similarly, we can see here this chlorine is going to attack the CH3 here. You can see the reaction. Now, that is halogenation. Now, let's see nitration. So, nitration is NO2 is substituted. So, the reagent we are using here is concentrated nitric acid, HNO3. So, you take propane, you react it with concentrated HNO3. What is formed? So mixture of nitroalkanes is formed when it comes to nitration. So it can replace a primary hydrogen, a secondary hydrogen, or radical mechanism. So like new nitroalkanes are also formed, like these two. Like we have seen here, right? Where many products are possible. So similarly, many nitroalkanes are also possible, and disproportionation can take place. Like now, if I have butane here, it can become into substituted propane like this, or it can also form an alkene. Okay, so these all are possible in case of radical mechanisms. So that is why a mixture of nitroalkanes is formed, and we don't discuss about reactivity that much. Okay, so this is reagent is concentrated HNO3. No, sulfonation. Sulfonation is SO3H is substituted. Here, the reagent we are using is fuming sulfuric acid or oleum. So they won't give like this, or sometimes they can even give like this: H2SO4 plus SO3. Okay, H2SO4 plus SO3 forms H2S2O7, or it is also called as oleum. So what is happening in this reaction? So H2S2O7 is reacting with the alkane we are having here, and it is forming SO3H. Okay, so SO3H is formed and it is attached to the tertiary carbon. So the reactivity is tertiary more than secondary, more than primary. This is the sulfonation process. So that's it with the basic substitution reactions. Now let us see oxidation reaction. So oxidation reactions, we are going to discuss two types of oxidation reactions here. So we have combustion reactions, we have controlled oxidation reactions. So combustion reaction is like you are going to heat it in presence of oxygen. So what would happen? The whole hydrocarbon is going to turn into CO2 plus H2O. So we have seen the combustion reactions in many cases. So how do you balance combustion reactions? So we have this formula, right? CxH5 plus X plus Y by 2 H2, sorry, O2 gives rise to XCO2 plus Y by 2 H2O. So using this, you can balance a reaction. So that is called total combustion. So delta H is negative, means the reaction is exothermic. Now we have another reaction called controlled oxidation. So in controlled oxidation, what would happen? We are going to use some reagent and complete combustion is not going to take place. Okay. So a little bit of various products are formed. So here we can see an alcohol is formed, here formaldehyde is formed, and then here alcohol is also formed. Okay. So when you are using copper catalyst, alcohol is formed. So when you are using this catalyst, formaldehyde is formed. So these reactions we will discuss in other chapters also. So just the remembering point in this oxidation, controlled oxidation is this KMNO4. So what happens in this reaction is, give me a minute. So the alkane, you are going to take an alkane and then you are going to react it with KMNO4, potassium permanganate. So it acts as strong oxidizing agent. So alcohol is formed here. So here tertiary alkenes can easily be oxidized than primary and secondary. So tertiary alcohols are formed. And we have a small topic called heat of combustion. So heat of combustion is heat released by complete combustion of a hydrocarbon. So heat of combustion is directly proportional to number of carbon atoms. So if you are taking some butane, it will have more heat of combustion than propane than ethane. Okay. Now we have some other reactions also. We have pyrolysis or cracking. So pyrolysis or cracking, when you are going to take a higher alkane, means it is having more number of hydrocarbon. I mean more number of carbon, and you are going to heat it in absence of it. What would form? Lower alkanes are formed. With lower alkanes, some alkenes are also formed. So this process is called pyrolysis or cracking. So we have isomerization reaction. So what happens in isomerization reactions? Isomer is formed. Means you are going to take an open chain compound, and this is the reagent important. Here reagent is important. AlCl3 with HCl. So with isomerization reaction, what would happen means the straight chains would convert into branched chains. So you can see an isomer is okay, isomer is formed. So straight chains are converted into branched chains, isomerization reaction, and the reagent is AlCl3 and HCl. You have to remember these reagents. And aromatization reaction. So aromatization reaction means you're going to take an alkene, you're going to throw some reagent, and then an aromatic compound is formed. So the reagent here we are using here is Cr2O3 Al2Cl3. Very important reagent. We have to remember. Even temperature is important, 600 degrees centigrade. So you are going to take an hexane. Aromatization reaction the mechanism is not important, but then also first this bond is formed, and then cyclohexane is again converted into an aromatic compound benzene. Okay, if we take n-heptane, what would be? It would be something like this. Like I'll just copy this. This- So this will be the n-hexane, and then a new bond is formed and aromatic compound is formed. So that is why toluene is formed when you are going to use the same reagent. So that's it. We are done with alkenes. We have seen all the chemical properties of alkenes in this video. That is, we have seen halogenation. We have seen physical properties. So boiling point is directly proportional to molecular weight. Melting point is also directly proportional to molecular weight. Even number of alkenes have greater melting point than the adjacent odd number of alkenes. And then boiling point, when there are more branches, boiling point will be more because of packing. And then density, solubility, chemical properties, we have seen halogenation. So halogenation, reactivity order is important. Fluorine is more reactive than chlorine, is more reactive than bromine. Okay, and then you need sunlight for chlorination and bromination. But when you are using fluorine, even sunlight is also not required. This happens even in dark. Okay, I forgot to tell that. This happens even in dark. So a mechanism, chain initiation, chain propagation, chain termination. In chain initiation, what would happen? The bromine bond is homolytically cleavaged, and then the mixing of these radicals are formed, and then at last all radicals combine to form products. So major product and minor product, we have seen the stability table. We have to remember this, the reactivity table: 1 3.55, 182, and 1600, 3.5 or 3.8. So how do you find the percentage product? You take the reactivity of the hydrogen you are replacing by total reactivity into 100. Okay, we have seen then we are also having Hammond's postulate, which is comparing bromination with chlorination. It tells that chlorination is exothermic and the transition state looks towards the reactant. In case of bromination, it is endothermic and the transition state will look towards the product. So bromination is more regioselective. Okay, and then when reactivity is more, the selectivity will be less. We have seen reaction with SO2Cl2, and then we have seen nitration, we have seen sulfonation, and we have seen oxidation reactions. And then we have seen isomerization and then aromatization. That's it. Alkenes is done. In next video, let's discuss about alkenes. Right. Thank you.